Hello, assalamu alaikum. How are you doing today, guys? Well, so far we talked about a few types of series and a few tests to check convergence and divergence. We talked about telescoping sum. We talked about geometric series. We talked about the integral test. And today we are going to talk about two more interesting tests. They are called the comparison tests. The comparison tests. Well, let me write the first test, which is we call the comparison test. The first one is the comparison test. Comparison test. And let's agree to use here CT for short. Okay? Let AN and BN be two sequences of positive terms. Let me write it like this. Let AN larger than or equal to 0, smaller than or equal to BN for all N. Okay? If summation Bn, n from 1 to infinity, is convergent, then summation An, n from 1 to infinity, is also convergent. That's the first statement. The second statement, if the smaller one, if summation An, n from 1 to infinity, is divergent, then summation An, n from 1 to infinity, is divergent. Well, it looks here, it is very simple. And indeed, it is. The only idea that you need to worry about or to think about seriously here is how you make the comparison here. Okay? So I'll come back to explain this further and to verify or to give here kind of rough proof of this test. But let's take an example to see how to handle that. Here is an example. If I ask you about this series, summation n from 1 to infinity, Ln n over n. Is this series convergent or divergent? Well, before this test, maybe you will think about the integral test. Remember, in the integral test, there is a lot of work that you need to do. You need to find a function. Your function should be positive, should be continuous, should be decreasing, and then you have to integrate, and you get improper integral. And so basically, there is a lot of work involved in the integral test. In this one, if I want to do this, I will make a comparison with this. Ln n over n. Now, if n is 0, if n is 1, this is 0, so I don't need to worry about that because you get 0, okay? However, if n is larger than or equal to 2, I can say this is larger than Ln2 over n for all n larger than or equal to 2. Correct? So basically, I don't worry about the first term because it is 0. So starting from 1 or starting from 0 here, it doesn't matter. And that is the reason here I said for all n. I didn't specify whether n is 1 or 2. In fact, you can start n here from any number you want, not necessarily from 1. Okay. Now, is this obvious to you? Well, Ln n is larger than or equal to Ln2, so this is very clear here. And always when we make the comparison, it should be very clear. And this is larger than or equal to 0. In fact, it is larger than 0. Okay? So when you make the comparison here, you have to be careful. Okay? So this larger than this, it is very clear, and this is positive. Now, we know summation. This is constant. Take it out if you want to. Is divergent. So if the smaller one is divergent, and it is positive, then the larger one is going to be divergent. Okay? It is like, you know that your friend is wealthier than a millionaire. Then obviously, he's going to be a millionaire. Okay? So now we know this is divergent. So summation L n n over n as n from 1 or 2 to infinity is divergent. Okay? This is our first example here. It's very simple. Using the comparison test is divergent, I can say here by the comparison test. Okay? Example 2. Summation n from 1 to infinity 2 plus sine n over, well, let me make this, okay, 2 plus sine n over n squared plus 5. Well, none of the tests we had before this can help you to answer this question or to find whether this is convergent or divergent. However, if you look here in the numerator, you have 2 and sine n. You know sine n is always between -1 and 1 here. So basically, you know the numerator is between 1 and 3 all the time. Okay? And in the denominator here, the boss is n squared. So basically, the dominant term is n squared. So here, you can think in your mind or in the margin that this is going to behave similar to this. And you know this is the P series, P is 2, so you know that is convergent. So from the beginning, you have kind of hint that this series is going to be convergent. The question is, how do you write the solution in a very formal, very organized way? Well, let's see here. Here we have 2, here we have sine n. So the numerator is always positive. The denominator is always positive. So we have 2 plus sine n over n squared plus 5. This is larger than or equal to 0. In fact, it is always larger than 0. And this is smaller than or equal to 3 over n squared plus 5. Is this clear? Yes, because sine n is less than or equal to 1, and here 2, that will be 3. Now, this is also smaller than or equal to 3 over n squared, because I have plus 5 here. So this is bigger than this. It means the fraction here is smaller, correct? This is true for all n larger than or equal to 1. And again here, that is clear. Always when you make your comparison, it has to be clear comparison, okay? Don't just do like random comparison, less than or equal, without worrying about whether it is true or not. What you write here should be valid. Otherwise, your solution is basically doesn't make sense, or you are building your results on something that is not clear or not right. All right, that's it. Summation, because summation 3 over n squared, n from 1 to infinity, is convergent, then summation n from 1 to infinity 2 plus sine n over n squared plus 5 is convergent by the comparison test. Look how simple is that. So here is an example about divergence. Here is an example about convergence. Both of them are easy examples. Okay? Now, let me take you back to the test itself. Can you think about kind of verification or a proof of this? Well, why it is like that? Well, the divergence should be very easy. Why it is very easy? Because you have positive, and you have this larger than this, and this is divergent. Okay? So basically it means here you are adding positive things and you get infinity. Keep adding positive things. Okay? So basically if you take the sequence of partial sums, Sn equals summation k from 1 to n, an. The sequence of partial sums is going to be monotonic. It's going to be increasing. You keep adding positive terms. Okay? So this goes to infinity. Divergent here, it means this has to go to infinity. Okay? And this is larger. So basically this has to go to infinity too. I mean the summation here has to go to infinity too. So divergence here is very easy to observe. What about convergence? Well, again, think about the sequence of partial sums. If you take the sequence of partial sums for Bn, and let's call this Sn star equals summation, this has to be k here, k from 1 to n, bk. Because it is positive, this is convergent. Now, well, I think I need only this. I need this. Sn here is monotonic. It is increasing. And because this one is convergent, so this one, the sequence of partial sums, it's going to be bounded. So if you think about the sequence of partial sums, it is going to be bounded and it is increasing. So it must converge. So basically this test here is easy to verify, okay, using boundedness and monotonicity. All right, let's give you more sophisticated examples about this. I'm going back to this example, and I'm going to change it and make it sine n squared here. Let's see, is it getting hard or is it still easy? Well, this is not obvious for you. Here you have ln n and here you have n squared. Well, let's try to understand the numerator here. If you think about the numerator, at 1 it is 0. And you know from calculus 1, this is y equals ln x. I mean, it's not asymptotic here, it keeps going up. Like this. Okay. Now, if you think about this, and you think about the line y equals x, here it is. Y equals x. So this goes below x. However, if I compare this with x, it will not help me too much here. Let me here compare it with y equals x to some exponent. Let's say instead of 1 here, let's say here 9 over 10. Or let me take this alpha, where t, and here t is a fixed, or you are used to c. Let me put c here. C, such that c between 0 and 1. So at 0 here you have 0, and then this is increasing because the derivative will be positive, the second derivative will be negative, so this is concaving up and it is increasing, so it's like this. And if c is close to 0, this could go down like this. So what does it tell us? Let's here take c to be close to 1. So here this tells you that ln is smaller than or equal to n exponent c for all n larger than or equal to some value n0. Now, this you can consider it as a fact. You can use your graphing calculator or any software to graph this and just convince yourself, if it is not clear to you, convince yourself about it. So here what I am saying is ln n is smaller than or equal to n exponent c, where c between 0 and 1. You can take c here to be close to 1 if you want to, like 0.9, okay? So what does that tell you? It tells you that ln n over n squared, this is positive, larger than or equal to 0, and smaller than or equal to n exponent c of n squared for all n larger than or equal to n0. It could be 2, it could be 3, it could be 100, but it doesn't matter because always you can cut few terms at the beginning. So I can write this n from 2 to infinity ln n over n squared as summation n from 2 to n0 ln n over n squared plus summation n from n0 plus 1 to infinity ln n over n squared. Now this you don't need to worry about it because you have finite number of terms, okay? So all we need is just to worry about this. Now if you look here, and this is between 0 and 1 here. Keep in mind, your c is between 0 and 1. Here you have n squared. So this, if you think about it, it is going to be 1 over n to some exponent. Your exponent is going to be, let me say here, k or m, where m is larger than 1 and smaller than 2. Correct? But in this case, we can use the because summation n from n0 to infinity 1 over n exponent p. Maybe I better use p here. Is convergent for all p larger than 1. Then summation from n0 or n0 plus 1 to infinity ln n over n squared is convergent by the CT, comparison test. So if you think about this, the tricky part is to use this. But after that, it is straightforward. Okay, now sometimes, as you observe here, when we compare, it is not easy to compare at the beginning, but we can compare later on. And in this example, it was after certain positive integer. But what if that is not clear at the beginning? So in that case, using this test will not be very helpful. However, we have another test. It tells us instead of comparing here from the beginning or after certain terms, just compare at the limit. How? That is the limit comparison test. Limit comparison test. And let's agree to use LCT, limit comparison test. Let AN and BN be sequences of positive terms. Be sequences of positive terms. Suppose limit AN over BN as n goes to infinity is L, where L is not, of course, because this is positive, so the limit either positive or 0 here. However, if this L is not 0, not infinity. And L is not 0, not infinity. Then either both convergent, then AN and summation BN, n from 1 to infinity, n from 1 to infinity, are both convergent or both divergent. Either both convergent or both divergent. Now, let's see how interesting is this test. Here is an example. Summation n from 1 to infinity, here n squared plus 5n minus 1 over n cube plus 10n squared minus n plus 3. If you think about this series and you want to use here comparison, how do you compare this here? You have negative terms, you have positive terms. So making here direct comparison, like the first test, that will be a headache here, okay? That will be difficult to do unless you start at some large n, but that needs some work to verify. Instead, what we think here, we think about the limit comparison test. And here from the beginning, you need to have a feeling about what's going on. And our feeling here is very easy to conclude. Look, in the numerator, who's the boss? The boss is n squared. In the denominator, who's the boss? It is n cubed. So basically, all you need is just to think about the boss in the numerator and the boss in the denominator. So n squared over n cubed is 1 over n. So right away, you have to feel or to get a hint about your series, and the hint is this series is going to be related to summation 1 over n. Okay? So now, what we need is just to think about this as an, and let Bn equals 1 over n. So let's see. Now, we are saying here it is a sequence of positive terms. Now, when you start here at 1, the positive terms here, they are going to kill the negative terms here, correct? So if you think about n, 1, 2, 3, 4, whatever, so the negative terms here are going to be absorbed in the positive terms. So limit an over bn, n from 1 to infinity, limit, not sum. Limit an over bn as n goes to infinity is, so divide this by this, what do you get? You get limit n goes to infinity, n cube plus 5n squared minus n over n cubed plus 10n squared minus n plus 3. Now, the first section we discussed, it was about limits of sequences. And you know here, this is similar to what you had in Calculus 1 when you talked about polynomials of degree 3, polynomials of degree 3. So basically, this is going to be 1. You know it right away. So the limit is L. L is not 0, not infinity. So either both convergent or both divergent. However, we know summation 1 over n from 1 to infinity, is divergent. So, by the limit comparison test, summation an n from 1 to infinity is divergent. Okay? So this series is divergent. All right. After understanding this example, let's go back to this theorem and let's see why it works like this. Well, all you need is to think about this limit. When you think about this limit, limit an over bn as n goes to infinity equals L, it means when n is very large, you are going to get an over bn is smaller than or equal in number that is larger than L, is smaller than or equal to m, and larger than or equal to a number that is smaller than L. So basically, between small m and big M, you have L. So that's the meaning of the limit. When n is large, it means you come close to L. And close to L here, let's say L between m and this small m. Now, this is going to be true for all large n. Let's say n larger than or equal to capital N for some positive integer capital N. Now, this will give you an between m, bn, and m, bn. Now, m is a constant, and capital M is also a constant. So now, you have this for all n larger than or equal to n. So what are we talking about here? We are talking about the comparison test that we already discussed. So if summation bn is convergent, and because here we are taking positive terms, so this is also larger than or equal to 0. If summation bn is convergent, then when you multiply by m, still it is convergent. And in that case, summation an is going to be convergent. Now, if summation bn is divergent, when you multiply it by small m, it's still divergent. And this is larger than this, so summation an is divergent. So basically, what you have here, it looks fancy, it looks sophisticated, but actually you get it from the comparison test. So here, the theory is not so complicated because the limit comparison test is in fact coming from the comparison test. And the comparison test is in fact coming from the monotonic boundedness theorem. Remember, every sequence, every bounded monotonic sequence of real numbers is convergent. Okay? So that is the theory behind those two tests. All right. Let's take another example here. Example, summation n from 1 to infinity, 1 plus 3 over n exponent n. Is this convergent or divergent? Well, sometimes when you are working on something, then what you are doing dominates your thinking. However, always you have to be ready to think out of the box. Okay? So here we are talking about comparison test and limit comparison test. Then I throw an example like this. So don't keep thinking about comparison test or limit comparison test. Always be ready to think out of the box. Okay? So here, it will be a waste of time to think about comparison test or limit comparison test. Remember the divergence test that we had about 1 week ago. Divergence test. If you take this limit, 1 plus 3 over n exponent n as n goes to infinity. What is this limit? This is e exponent 3 that is not 0. So by the divergence test, this series is divergent. Is divergent by the divergence test. Okay? So again, just I put it here to stress that always you have to be ready to think out of the box. Don't just keep thinking about what you have in front of you. Okay? All right, let's take this example. Summation, sine 1 over n, n from 1 to infinity. Can you do this one? Well, are you thinking about the divergence test? Well, if you think, you get 0 here. So basically, the divergence test doesn't help you, correct? If limit a n as n goes to infinity is 0, then the divergence test does not help you. Okay, so in that case, what do you think of? Geometric series, that's not a geometric series. Telescoping sum, this is not telescoping sum. Integral test, this is a fluctuating. So, I mean, if you want to use the integral test, it will not be easy to use. Well, actually, when in between 1 to infinity, this will not be fluctuating. But doing the integral is not easy. So the only test you have now is either comparison test or limit comparison test. Now, if I take this as an, and I take bn to be 1 over n, this, when n between 1 to infinity, this will be small. This will be between 0 and 1. So basically, this is positive. This is positive. So limit an over bn as n goes to infinity is limit as n goes to infinity sine 1 over n over 1 over n. What is this limit? When n goes to infinity, this goes to 0, this goes to 0 at the same rate. So basically, that is similar to sine n over n when n goes to 0, or sine x over x when x goes to 0. And this limit, you know it from calculus 1, it is 1. So that's it. L is not 0, not infinity. We know summation 1 over n, n from 1 to infinity is divergent because this is divergent. Then summation sine 1 over n, n from 1 to infinity is divergent by the LCT, limit comparison test. Okay? So here we started by very simple examples. Then later on we discussed kind of more sophisticated examples. Let me ask you to do this one as a homework. You have several exercises in your book, but you can do this one. Do this as homework. Summation en plus 1 over en plus 1, n from 1 to infinity. All right, so this is it for today. Please do this exercise, then do the exercises that you have in your book. And if you have questions about that, you can get in touch with me. Okay? All right, so that's it for today. Have a good day, guys. Bye-bye.